Next curve.
Hey everyone, welcome to this episode of the Next Curve Rethink podcast. And of course, this is our special Silicon Futures series, which I do in partnership and collaboration, wonderful collaboration with the illustrious Karl Freund of Cambrian AI and soon to be quantum research.
It became quantum, I think. It's the next big thing.
Yeah. And then, of course, the quantum Dottie.
Are you ever going to run out of
McGregor
for me?
Jim McGregor of Tirius Research.
Clan McGregor.
Yeah, okay. Clan McGregor. Yeah, who has some amazing kids who are just remarkable programmers. I don't know why I'm saying this, but I just feel like saying it. I saw Damien, by the way, at Cadence Live 2026. And yeah, you have really cool kids, man.
Thank you.
Yeah. Anyway, welcome everyone. And, of course, we cover all the exciting stuff that you need to know in the world of semiconductors, AI, and apparently now quantum. Yeah. Quantum. And so this is going to be a really exciting episode because Jim and Karl have been going deep into all this quantum stuff that everyone is starting to get pretty excited about. And they're going to basically break down the landscape. And so this is going to be a great education for me. And these two gentlemen are going to basically lay it out. This is what the landscape looks right now. And this is sort of how you need to structure your thinking around what the market will look like and how the competing technologies actually, right? There are many different approaches, how those will likely and maybe play out in the future. And so this is a really interesting area. It's formative, I believe. I don't know if you both agree, but I'm really excited to have this presentation by the both of you on this emerging, well, do you want to call it an emerging topic, or is this just something that is hot, but people need
it's one of the most important topics for the next decade.
Yeah, absolutely. Totally agree.
Yeah.
And then we get into neuromorphic computing, so we can do even more there.
Okay. Yeah, we'll have another talk on that, right?
We're going to make his head explode, Karl, if we keep doing this.
Yeah. But you know what? For those of you who are listening on audio, you really want to go to YouTube and watch it because watch this episode because we're going to have some graphics. And if you follow us on LinkedIn, when we post on LinkedIn or other social outlets, we'll provide the presentation material. But for those of you who are just listening in, you really want to check out the YouTube episode and the video so that you can see the charts that these two gentlemen have prepared. And they're quite pretty. You guys did a very good job. Yeah, well,
Thank you.
Are pretty too. You guys are very gorgeous in that regard. So,
well, when you have a face for radio, you have to make your slides look good.
That's a good one. Right. Okay. So on that note, before we get started, please remember to like, share, and react, and comment on this episode, and also subscribe here on YouTube and Buzzsprout. Listen to us on your favorite podcast platform. Opinions and statements by my guests are their own and don't reflect mine or those of Next Curve. Although I think we're going to be in very good alignment since you guys are really going to be giving a master class here. So I'm all ears, and I think the audience will be as well. And opinions and statements, like I said, are their own, but we're doing this for informational purposes. And in this case, it's educational. It's going to be great. And we do this to provide an open forum for discussion and debate on all things AI, semiconductor industry, and now quantum. And so with that, gentlemen, hey, where should we start where should we start this conversation about quantum?
Let me start with mine, if that's okay. They're a little higher level, and Jim gets into more detail. It's actually been a big week this week, or last week, I guess, since we posted next week, because this week was World Quantum Computing Day on Tuesday, right, Jim?
Yeah, supported by NVIDIA. Yeah, it was NVIDIA's quantum computing day.
NVIDIA had their second quantum day, not associated with GTC this time. It was a standalone event with Jensen Huang speaking and some of the leaders in quantum. That are, at least those that are friendly with NVIDIA were there. Those that are not as friendly weren't there. But it was really great. NVIDIA made some important announcements with their new quantum model for basically improving the error detection and error mitigation correction. The problem when an error happens, where did it happen? And that's where GPUs can help quantum a lot. So there's a really emerging view that GPUs and quantum are not going to be competing technologies. They're really going to be collaborative technologies that help bring quantum to the useful quantum computing era. So what I've done here is just created a slide, because it gets very confusing for all of us, of what is going on in this marketplace. And how can you have this many billions of dollars pouring into a market that's currently producing, call it, zero revenue? But as Jensen Huang says, the most interesting markets are the markets of $0 that will grow into billions of dollars. And many of us are firmly of the belief that that is exactly what will happen with quantum computing. It's not going to replace AI. It will facilitate AI, and AI will facilitate quantum. It's a nice reinforcing cycle here. It's a virtuous cycle. So on the left, you have the modalities. And by modality, I basically mean what kind of physics are these guys using to create these quantum states? And the next column is basically in plain English, how does it work? What's this stuff all about? Next column is key companies. And then finally, the maturity level. This is not a grading level. This is saying how close are they to producing quantum advantage. By quantum advantage, we mean that you can solve meaningful problems in a cost-effective way that you cannot solve in digital computing technologies, regardless of how big your supercomputer is. So let's start. I'll try to do this quickly. You have superconducting qubits. This is the one that's been around the longest. This is where IBM and Google and Rigetti, as well as IQ and OQC, this is where you see those huge chandeliers of gold that are used as the final stage of cooling that creates a temperature of millikelvin. So this is colder than outer space. And that is where the actual superconducting chip, can operate. And so you have these back rooms full of these huge refrigerators that eventually chill down through these chandeliers to the bottom where this chip is going to operate. The advantage of this technology is it's really fast. The disadvantage is it has to operate at ultra low temperatures, which is very expensive in space. It consumes a lot of space. But it's also unfortunately very noisy. So if you think about a normal semiconductor chip, it's okay that you're at 10 to the minus seventh in errors per compute. That's okay. But here we're talking about 10 to the minus 2 or 3. So that means one in 100 or 1 in 1,000 results are bad. And considering you're producing hundreds of millions of results, that's not good. So you have to identify these errors, and you have to mitigate these errors, which means reduce their impact. But you also eventually have to correct these errors. This is often done by teaming together physical qubits to create a logical qubit, the ratio of which is super important to both speed and economics. If you can do 2 or 3 physical qubit to produce 1 logical qubit, you're going to be 3 times more powerful than an architecture that maybe takes 10 logical qubits or 100 logical qubits to produce one, physical qubits to produce one logical qubit. Logical qubits are what matter. If you try to distill it down and across all these modalities, logical qubits and their performance and cost are really what matters here.
It's what you're using. It's really what you're using to form the gates, the circuits, those quantum circuits that you're actually developing. And by the way, if you've never seen pictures of the Poughkeepsie Supercomputing Center in New York that IBM has, it kind of looks like an invasion of the body snatchers. With all these hanging refrigerators.
All these hanging refrigerators. They're huge. They're huge, as well as at the T.J. Watson Research Center, where they have a major demo center now, demonstrating the IBM Quantum System 2. Now, if you go down the list, trapped ions kind of nest. These are kind of they're not random orders here. These are kind of in decreasing state of maturity, potentially increasing potential to be disruptive. Trapped ions are much more much higher fidelity, which means that they're not going to be as error prone, but it's hard to scale. That's in progress, and it's hard to get the performance. They don't have the same performance as a superconducting circuit does. These ions, they're exotic ions. I can't even remember their names. They're not normal elements you'd think of. They're trapped in control with lasers. And walking around the computer show floor at, let's say, GTC last month, you could actually see models of what these look like. Very high fidelity. There's got to work on performance, and you can see the companies that are listed there. Neutral atoms, kind of a dark horse here, is late in development, but is showing tremendous potential, tremendous promise, because they operate at room temperature. You don't need these massive refrigeration systems to get them down to sub 1 degree Kelvin. So that means they're a lot more portable. They're more affordable. They're more flexible, and they're fast. They're not as fast as superconducting qubits or even as trapped ion qubits, but they can be as fast when you combine them. Because of the cost, you combine several physical neutral atom qubits to create a logical qubit and get pretty much the same performance. Photonic is using light particles, and you can see some of the companies there that have been quite vocal about their ability. They're, again, kind of like neutral atoms, early days, but very promising technology. The next one is spin qubits, or quantum dots. These are electron spin in a semiconductor structure. And you can see the companies there, the most notable are probably Intel. Again, this is early stage. This is not something you or maybe even your children will be using, but it does have a lot of potential.
We should note, though, that Intel actually started on supercomputing, and then switched to the spin bits. So right. So a lot of you have to realize that this is all been in development stage. So some of these companies have actually evaluated or worked on multiple different types of these different qubit solutions.
Quantinuum is like that. Quantinuum used to be known as Honeywell.
It used to be part of Honeywell.
It used to be part of Honeywell, and they spun them out, and they really decided to focus at that time on trapped ions. But before, they were more of an application layer and really trying to develop independent of the modality. They decided to just focus on trapped ions. They think that's the sweet spot.
So, Karl, some of the audience might be wondering, well, as you go down this list, at what point are you departing from superconducting and supercool, like this near 0 Kelvin cooling? So what does that look like here? Because you mentioned neutral atom is room temperature, right? And so, what are we looking at in terms of the environment that these different modalities outside of the supercomputing operate in?
Well, it's actually supercomputing and the quantum annealing that use the ultra low temperatures. Everything else is either a higher temperature or at room temperature, especially when you start talking about using photons or ions and stuff like that.
Right. Okay.
Yeah, exactly.
All right.
Quantum annealing is kind of a niche. It has commercial uses today, and there's really two players there, D-Wave and Fujitsu. And then there's topological qubits, which created a tremendous roar in the market when Microsoft disclosed it. They're the only ones doing this. If they can make it work, which is a big if they can make it work, it could be the winner, but it's very far from production and the least developed research platform.
Yeah. But it was pretty amazing at the time how much buzz it created. But and earlier you mentioned you said supercomputing. You meant superconducting. I
meant superconducting.
Right? Superconducting.
Yeah. Right. Okay. All right. Just wanted to clarify that.
Thank you, Leonard.
Yeah.
Okay. Some of the pros and cons here. I've probably covered quite a bit of this already.
Yeah.
Pros of superconducting, fast gates, very strong ecosystem, by the way, because they've been around a long time, and IBM is willing to spend a lot of money to facilitate the collaboration of research institutions around the world. It's the near-term leader, right? Big, strong force in the industry. Trapped ions, they're really the contender right now for fault-tolerant systems. Neutral atoms, they're the dark horse. But there is one company, for example, which is Inflection, did a SPAC in February. And so they're now publicly traded. And they're seeing a lot of interest from investors in neutral atoms. And they also have an existing business, which is called quantum sensing. We're not talking quantum sensing here, we're talking quantum computing. So they can use that to fund and finance their development of quantum computing. Photonic, very strong for quantum networks and distributed quantum computing. Quantum dots, promising long-term pathway for building these on silicon, on CMOS compatible chips. Topological, potentially a breakthrough. Very high risk, very high reward. There's quantum annealing. It's commercially viable today. D-Wave's doing quite well in their niche, but it is a niche. It's not going to be a general purpose quantum computing. With that, I'll turn it over to Jim, and you can dive into your analytics, Jim.
I took a similar view to what Karl did, and I have to kind of preface this and say that, all these numbers are relative. In other words, they're things that they're how I kind of we're going to go up one slide, but how I kind of positioned the different factors of these different technologies. And quite honestly, you have to remember that all these technologies are still developing, so they are changing and they will change. So even looking at this spider or radar graph that you're looking at, all these different technologies will change over time. And if you click down one slide here, we'll see, when you start looking at the numbers and you start looking at how they're positioned, supercomputing kind of provides that best balance. Trapped ion provides that high performance solution, or the best performing solution. The photonic and quantum dots, which are very similar, have the best manufacturability capabilities today. Although the topological, that was the one that Microsoft is working on, is theoretically the best from an error correction standpoint or error mitigation standpoint. So it will be very interesting. And then once again, that annealing is really a specialized niche. I don't ever see that necessarily being a general market capability. And one more slide, I kind of outline some of those, the same thing that Karl did. But you have to remember, one thing you have to really remember, and let's go to the next slide, Leonard.
Leon. Is that
I said Leon, but I
that my Scottish don't know. Name?
Yeah, exactly. No, you have to remember where we are, and the fact that a lot of people have said, well, think about where AI was in like 2015, before everything kind of exploded. We're kind of there in what we call the NISQ era. It's kind of noisy and unstable qubits, where we're really still learning about it. But you have to understand that the industry has actually been working on this since the mid 90s. I mean, this is a technology it's taken. So when everyone says, "Oh, it's going to be decades away," it's been decades. This has been in development for a long time. I mean, we went through a long period of just understanding, is this even feasible, and then kind of proof of concept era through the early 2000s, and now we're in an era where we understand it a little bit better. We're having to do a lot of error mitigation and suppression just to be able to get rid of some of that noise that's in these different types of qubits. And obviously, there are many different ways to create a qubit and read a qubit. But we've created quantum utility. And this is probably the most important thing. Why are there billions and billions of dollars going in this? Not just in terms of the technology, but also in terms of the use of it. I mean, you have banks, you have materials companies, you have scientific research organizations all pouring billions into this because they see this as a very significant leap in terms of computing. This is an accelerator technology. It's not going to displace classical computing. And this is why AI and standard computing and basically the accelerated computing environment we're in now is going to be so beneficial to this, because basically it's going to help us on the front end basically create the quantum circuits to organize the data and everything else that feeds into this quantum accelerator, and then understand that information and do any error correction as it comes out of that quantum computer. So basically this quantum computer, or QPU, quantum computing unit, is going to be another type of rack that sits in the data center, or even maybe remotely, that's tied to that standard supercomputer or AI powerhouse. And right now we're finding that, even when you get to like 100 qubits, and that's physical qubits, you're getting into an area where it's starting to be interesting, where you can understand how to use the technology, and even run some interesting simulations. And when you get to 1,000 physical qubits, then you're getting into an area where you're creating a significant number of logical qubits, maybe 100 or 200 logical qubits, creating gates, creating circuits, and actually exceeding that capability, as Karl said, creating quantum advantage where you're exceeding that capability of even what a supercomputer or any supercomputer on the planet can do today. Now, you have to remember that there's always a probability risk here in terms of, how close to an actual answer it is. But you have to remember that what it's trying to do is beyond what we've been able to do before. Analyzing the human genome, modeling the Earth and the weather patterns, actually discovering new material technologies. It's very, very significant. And we're already getting to that quantum utility, being able to use this quantum technology. And going forward, we're really looking at this era that we're calling fault tolerant era, where basically we understand the qubits a little bit more. We can control the fidelity of the qubits a little bit more. And once again, this could be in any of those different modalities, but we get to a point where the accuracy is fairly high, and we're getting to a point where we can scale. And that's probably the most important thing. So when you see these rapid things, I mean, we're basically doubling to quadrupling the number of physical qubits that we can do every year, depending on the different modalities. That's significant because we're going to be able to go from, thousands of qubits today, or hundreds to thousands of qubits today, to millions of qubits shortly after into the next decade. Some place it between 2032 to 2035. We place it somewhere around 2034, but that's very significant. And once again, as Karl said, once you get into that range, and you're only doing anywhere from, it could be a couple physical qubits to 100 qubits per logical qubit, you're still getting into a point with 1 million physical qubits to where you can do some very significant things that you couldn't do anywhere else or any place else.
And in fact, all the companies we've mentioned all have roadmaps that explain how they will get to 1 million qubits, which is sort of the milestone for quantum advantage. There'll be some areas that can actually get to quantum advantage at far lower numbers of qubits, but in terms of a more general platform for doing scientific work and research in areas that we don't touch today because today's computers simply can't do it. So it's going to open up all kinds of areas of computational applications that do not exist at all today. So
And
it's funny. Some people talk about how, there was an article about 3 or 4 months ago, some guy wrote, I think it was in the Wall Street Journal, that, that computing's all going to come down to the size of a shoebox, right? And it's all going to be quantum and stuff like this. And I'm like, well, I don't know what this guy's smoking, but I'd like some. It's crazy. It's crazy. This is not going to replace the traditional computers. Traditional computers will help.
Karl's address is no.
Yeah, and you know what? I think that was like one of that is one of the biggest clarifications that needs to be made at the moment, because I think there are so many misconceptions about what a quantum application is. And one of the things that was very clear from Quantum Day, and I managed to get listening on some of it, and I'd love to get both of your takes on this, but for the most part, the best way of thinking about what these applications are the ones that are traditionally, for supercomputing, right? Whether it's for scientific
very discovery,
much so. Right? Certain,
doing that analysis, doing the scientific research, doing those types of applications. And quite honestly, I don't know how you feel, Karl, but I think that, it's very much like AI modeling. I think we're going to end up with different types of quantum modalities for different types of applications. I think we're going to find as we get farther down the road that, and some of this is definitely AI enabled on the front end and back end, that we're going to be able to do, certain modalities are going to fit certain applications better than others. And and also the fact that, in looking at this chart specifically, that growth chart, it gets to a point you have to remember that, this is very much like the AI was, over a decade ago. We're going to see changes in the industry. So we're probably going to see a consolidation. Some of these companies will get bought for their IP or bought all out. We may have larger companies doing multiple modalities by the time we get to this fault tolerant era. So there's going to be a lot of change, and that's why everyone really needs to pay attention, because we don't know what the end solution is going to be yet.
Yeah, that's.
And are you saying there's going to be kind of a Cambrian explosion? No, sorry,
couldn't resist, could you?
Couldn't resist. Sorry, my bad.
So, quantum explosion.
Self promotion. My apologies. No, I agree with what you're saying, Jim. I think we'll see specialization start to occur. Right now, we're just trying to get to the point where we can demonstrate quantum advantage across a reasonable number of universe and spaces. But as it becomes more general purpose, you'll then see it specialize, and you'll see specific quantum modalities being used for certain problems and others being used for other problems. So I think there's room for all here to succeed. And quite honestly, there's plenty of money to be made by all the players, not all, but most of the players that we're seeing today have a significant research and results that will turn into competitive advantage in specific areas.
Yeah.
And there's one other area that, since you brought up the misconceptions, the other misconception we have to kind of address is that quantum is going to break everything. It is definitely a threat, because traditional security algorithms can be broken by a quantum computer in record times. Yeah. However, you have to remember that IBM, especially, that's been kind of leading the charge on these NIST algorithms that basically to actually kind of create algorithms that quantum computers can't solve for new security algorithms. They've been working on this for over a decade, and they continue, and these new NIST algorithms keep coming out every year, every couple of years. So quantum computing is not designed to be an encryption, to be a hacker's goldmine, but it is something that every company today has to be aware of and has to start thinking about, integrating these NIST algorithms, because they need to be quantum safe today. Because there is the theory that, and I completely believe this, you can go and scrape information today and possibly use quantum computers tomorrow to actually decipher the security algorithms. So that is a part of the quantum discussion. It's not the part of the quantum discussion.
Yeah. And I think that maybe that's a topic that we talk about separately, because one of the risks going forward is that, especially around this, quantum era security problem, that some of the thinking is based on, fundamental misconceptions about quantum, and I think you guys are doing a lot of good work that will be a basis of clarifying a lot of those misconceptions, because I think quantum computing is in general not well understood. They think that, for instance, quantum computing will displace and replace accelerated computing, right? And that's not the case. And traditional computing, as you both, cited before. So anyway, one of the things that I think might be a good clarification and education for the audience might be helping them understand what is the role of accelerated computing vis-a-vis quantum computing. Jim, you mentioned that AI will be important in enabling and scaling, helping quantum computing to scale. There was a lot of talk at Quantum Day, actually last year, about how AI and accelerated computing could enable or be a foundation for these control planes for these different modalities of quantum computing runtime. So, I mean, how does this all kind of interrelate with each other? Because you do have NVIDIA obviously making big investments in the quantum ecosystem, but also positioning their technologies for quantum computing enablement. Maybe both of you can take some time to stitch that picture together for the audience.
Well, you have to remember that we're dealing with quantum mechanics, so we're actually dealing with physics and physical systems here in understanding quantum computing. You have to remember that classical computing has always been a part of that, but also has some manual tasks, like actually trying to calibrate the qubits, actually trying to make sure that they're going to perform the way you hope they're going to perform, because they're always in a state of flux. And that's a huge, huge challenge. So, I mean, NVIDIA, and I credit NVIDIA for this, instead of trying to jump into the quantum computing fray, they've said, listen, we're going to enable it. We're going to be the key enabler here. So they've created their NVIDIA icing models to help with that calibration on the front end, to basically hopefully automate that to where it's not a manual process, it's an automated process and a reiterative process for each run that you're running, but also on the back end for doing the error correction, which as we've mentioned before, just getting the right information, ensuring that you have you have accurate information is a challenge today. We're using a combination of suppression, mitigation, and error correction today. We hope we get to, and that error correction really isn't that great at this point in time. So we're hoping we're going to get to a point where we have more steady states of the quantum, of the qubits, and B, so we have higher fidelity, and B, we get to a point where we can actually do quantum error correction with a very good understanding and very high speeds to be able to do that. So, I mean, NVIDIA, and this is a perfect application for it, trying, taking these multi-parallel solutions, basically they're GPUs, and saying, listen, just like we power AI with this parallelism, we can power these tasks in the front end and back end of quantum computing. So, and I credit them because I think it's going to be, what they're doing is not important for one specific modality or one specific partner. It's going to be important for the entire industry in any modality that's out there.
Yeah, I think I agree. Hats off to NVIDIA for really putting themselves at the center of the conversation of quantum computing without having a quantum computer. That's pretty magical accomplishment. I do kind of wonder how they're going to monetize that going forward, but they'll sell enough GPUs it will definitely help them. But more importantly, it puts them at the center of the ecosystem for most quantum computing, because everybody has to do error correction, everybody has to do calibration, calibration, and so that's an important first step. I don't think it's the last step.
Yeah. Well, I like both of your reactions to the comment that I'm going to make right now. I actually, the way I view it is NVIDIA is doing a really good job of positioning themselves in practical terms, right? Not just fluffy marketing terms as the picks and shovels for quantum computing. So this hockey stick that you have here, Jim, the concept is that they will be able to provide that control plane and enable these execution environments, the design of these execution environments so that quantum computing can scale, right? The other thing that I also noticed from conversations coming out of and presentations coming out of Quantum Day is that, accelerated computing is great for discovering applications, right? Because some of these applications are not known, and it's not that you're going to use quantum computing to figure those out. You actually need to have, accelerated computing, if you will, or AI to support that discovery process, much like what we see with drug discovery, right? So there's a role there, and your comment or a question, Karl, are the likes of NVIDIA, because I assume that there are going to be more players than just NVIDIA in this game. How will they monetize? Well, they would monetize by supporting these important activities in not only scaling quantum computing itself in terms of progressing all these different modalities, but also the discovery of the applications, but then also the design of the systems, right, and the circuits. That was the other thing that I took away as well. So I don't know, am I off base? Tell me that I'm wrong, and tell me
he's really leaving himself open on that one.
Yes,
I don't know where to take this.
Fire. Open fire.
I'm you know what? I'm leaving myself out in the open. You guys take shots. Go ahead. Knock yourselves out.
No, I think in general you're right. It was a really interesting article. I believe it's Wall Street Journal this week. Got to remember my sources better, but it was talking about how Jensen's investment strategy is not to pick winners. Don't pick winners. Mm-hmm. Invest in everybody who has a shot, and eventually you'll hit one or two that really give you a good return on investment. And I think that's what he's doing right now with quantum. He's saying, look, I don't know which one's going to be best. In fact, I don't know which ones are going to be best at which problems, to Jim's point earlier. So I'm going to invest in all of them by giving them the tools they need to accelerate fault-tolerant computing era. Get there sooner. Get there with higher quality qubits and lower cost. Right now, cost is not in the equation, right? It's just, can you get there? But eventually, if you can get there, well, then what will determine the winner is, well, how much it costs. And how manufacturable is it, and how high quality is it, how dependable is it, all that stuff, right? All the abilities will come into play, but right now capability is king, and so he's investing in everybody, and expects to be able to make money along the way.
Karl, you're getting soft. I'm out in the open. You can take a shot. Come on.
One of the interesting things is that, with any new technology, there usually comes new business models. And we don't know what those business models look like at this point in time. That's going to have to evolve over time. And, and like NVIDIA, we saw them kind of do an end-to-end solution for AI. We see IBM doing the same thing for quantum computing. They're probably the only company I know of that has, D-Wave and others, but really, most of the modalities are relying on kind of ecosystem partnerships to go through there. And I'm not knocking that. I think that's great too. But IBM put so much in end-to-end, from the refrigeration solutions to the systems to the wiring they have invested billions and continue to in the entire thing. And now they've got a partnership with AMD. Yeah. If you don't know, these two companies have worked together for decades. on copper interconnects and silicon on insulator technology. I mean, they have helped pioneer, these two of these companies have helped pioneer some of the major breakthroughs we've had in semiconductor manufacturing and design over the past 3 or 4 decades. So having those two work together, I think is going to be is going to be a big opportunity. And trying to see because once again, now you've got another AI company that's in the fray there. And it'll be interesting to see how everything kind of meshes together as we get farther on down the road. And it's funny because some of the quantum computer companies are promoting on-prem systems. I don't know if that's going to be the preferred business model. I still think that for the vast majority, cloud-based kind of rental solutions are probably going to be the most likely scenario for quantum computing, especially for the next decade.
Yeah,
well, I think the exception to that's probably in two areas. One is in financial services, and the other is government. If you look at a lot of these companies right now, they have two primary markets, customer segments. One is researchers, and the other is national defense. Mm-hmm. And so both of those areas, I think there is a role for on-prem quantum computing, even though it may be an internal self-hosted cloud. So kind of a hybrid model.
Yeah, and it's important to note that there's obviously a lot of investment from the research community too. Matter of fact, IBM has been putting some of their systems out there in the research community, like I believe the University of Cleveland or something like that. Or they've got to be universities and research organizations around the world now. So it's going to be interesting to see how this all plays out. And matter of fact, two of the companies are spin-outs from Oxford University. So I think we're probably, maybe not to the point where we saw transformer models and we saw LLMs with AI, but we're getting there very quickly. And by the end of the decade, it's going to get exciting.
Yeah. Sounds a lot like supercomputing.
It is. It's supercomputing on steroids.
Steroids. Yeah. It's quantum computing. Yeah. So Karl, do you think we're going to have quantum factories?
Quantum factories.
It sounds like Jim described quantum infrastructure, right? The whole supply chain and the build out of large data centers or quantum centers, and
yeah, I think there will be quantum factories because the cost of these systems is still quite high, and so you need to amortize those costs over as many use cases and customers as you can. And so building quantum factories where you have CPUs, GPUs, XPUs, and QPUs all basically providing services for applications we can barely imagine today.
Yeah. Okay. Now, this has been great. This has really been informative. I know I've learned a lot from both of you in this 30 minutes or so that we've had this chat, and it's great to have an opportunity also to talk about Quantum Day. I thought it was a really well done program. So hats off to
even some of the detail they went into was incredible. I mean, I need to go back and watch it probably a dozen more times to catch some of the mathematics, especially in the last presentation.
Yeah, I was in transit. I was trying to listen to this stuff as I was on a flight. So
the professor from Israel was just, oh my God, his mathematics depth was incredible.
So, gentlemen, thank you so much. Thank you so much. It was really
our pleasure.
Really, really great stuff, and I think the audience will undoubtedly find it incredibly grounding and a good orientation as to how they should view the Cambrian explosion. That is
quantum explosion.
The what?
The quantum explosion.
The quantum explosion. Nah, I gotta make it Cambrian.
Cambrian
quantum explosion.
I've got all these
the QC.
I've got all these Cambrian fossils. I can't change them all to quantum fossils.
There you go. Yeah. So thank you, gentlemen, and everyone. If you're interested in tapping into Jim's research, Karl's research, reach out to both of these gentlemen and their respective firms. Of course, Jim McGregor is with Tirias Research. How's that?
It's pretty good.
Pretty good, right? Yeah. I mean, hey, I'm an honorary Scotsman now because my nickname, or at least my Scottish name, is Liam, right?
Yes, exactly.
I got to live up to that honorary designation. So yes, reach out to him at Tirias Research at www.tiriasresearch.com. He's also on Forbes, and he's quite active.
Times and other publications.
Yeah, the list goes on and on. And then, of course, we have Karl Freund of Cambrian Quantum /AI research.
We keep putting hyphens on the company name.
Cambrian AI quantum research.
Yeah. So catch him at www.cambrian-ai.com. Right? Did I get that right?
That's right.
Yeah. And then, he has a Substack. He has he's on Forbes, and he's on LinkedIn. He's also well published, across a number of publications and outlets. And of course, please subscribe to our podcast here. We do an episode every month to cover everything that's happening that you should know about in the world of AI, semiconductors, and quantum. So make sure to check us out on YouTube, subscribe, like, share, and then check out the audio version on Buzzsprout, and listen to us on your favorite podcast platform, and subscribe to the Next Curve research portal at www.next-curve.com for the tech and industry insights that matter. Gentlemen, thank you so much. This is awesome.
Thank you.
We will see you at the end of the month, right?
We'll talk to you soon.
Yep.
Yeah. All right. Cheers.
Cheers.